Hi, this is Ziwei Liao. I am going to present multi-view 3D object reconstruction and uncertainty modeling with neural shape prior. This work is co-authored with Steven Waslander at Toronto Robotics and AI Lab, University of Toronto. 3D object reconstruction from monocular images is important for thematic scene understanding. We formulate the problem as that, given multi-view uncalibrated 2D images of one object from a specific class, for example trails, estimating the 3D shape representation of the object. It is challenging with no depth information, unknown poses, and corrupted observations from noise and occlusions. A category like trail has diverse shape variance. A 3D object representation is a high-dimensional output. All those add difficulties to the task. To address the challenges, we aim to model uncertainty into 3D object reconstruction. First, we want to represent uncertainty in 3D shape, which is critical for safety and downstream tasks. Then, we want to leverage uncertainty for multi-view fusion. It can maximize the usage of the multi-view observations and make system more robust to corrupted observations such as occlusions. Further, we want to leverage the category-level prior knowledge learned in a neural network. Conventional methods reconstruct from scratch with geometric consistency, such as structure from motion or SLAM methods, while human vision is capable to infer with prior knowledge from the memory of thousands of trails that have been seen. In the same time, the generative models have achieved remarkable performance to learn the distribution of multimodality data, such as images, texts, and also include 3D shapes. They can be used as prior to reconstruct from sparse or single views and fill in the missing parts. In the literature, we have different ways to represent 3D object models. Among them, signed distance function SDF shows the ability to model 3D surface as a continual function, which forms the basis to model shapes with neural network. There exist multiple works to use geometric constraints for 3D reconstructions, such as SLAM and structure from motion. However, they need dense observations to cover the scene and objects, or require a predefined object dataset, or only output sparse representation, and lack the usage of prior knowledge. Learning-based methods regress the 3D outputs directly from input images. They rely on 3D training data, have limited generalization to unseen data, and have quantization error for the shape. Neural implicit representation uses continuous neural networks to regress functions for 3D geometry. NERV has achieved remarkable performance for modeling the scene, while it needs to train a new network from scratch for each scene. DeepSDF shows the ability to use one neural network to model a category of objects, while it misses the representation of uncertainty. Based on DeepSDF, Frodo infers 3D objects from multiple images, while it is sensitive to corrupted observations since it equally views its results from different views without an awareness of the uncertainty. Uncertainty modeling has been investigated in the deep learning literature, such as object detection, thematic segmentation. There are multiple methods to model uncertainty. While modeling uncertainty for 3D tasks, especially for neural implicit representation, is still under investigated. We propose a new framework for uncertainty-aware 3D object reconstruction. It consists of three main components: uncertainty-aware shape decoder, uncertainty-aware image encoder, and multi-view fusion. We start with the shape decoder. DeepSDF proposes a method to model a category level of shapes into latent space. Given any 3D points, we train a neural network to output its SDF value. Given another latent code as input, we can control one network to output a category of instances. We further introduce uncertainty into the latent space and model the function outputs as the distribution of SDF value. Compared with the deterministic shape, our method decodes a latent distribution into a shape distribution which forms the uncertainty. More specifically, we first model the distribution of latent code as a Gaussian distribution and propose a method to propagate the distribution from latent space to 3D SDF space. The challenge here is that the decoder is a highly nonlinear function. We need a way to propagate the Gaussian distribution through the nonlinear function. We use Monte Carlo sampling to propagate the distribution. We sample n latent codes and calculate the corresponding SDF values separately, and form a distribution with a sample mean and a sample variance for SDF in the 3D space. The remaining question is how to estimate a latent code distribution from images. We use an encoder to estimate latent code distribution with mean and sigma, and train the network on a synthetic dataset. Where multiple images are available, we can fuse them in the latent space. Compared with fusion in 3D space, it's highly efficient and decoupled from pose. It also has generalization ability to different texture and background. The fusion can be naturally modeled with Gaussian update to get a fused mean and variance of the latent code. By then, we are able to get latent code distribution for each input images from encoder and fuse them with Gaussian update and decode the final code distribution into SDF space and use the Martin cube algorithm to generate a mesh with uncertainty. We follow a theme-to-real training strategy. We render synthetic images from ShapeNet datasets and randomly augment the backgrounds to train the encoder. We also train the decoder on ShapeNet dataset. Then, we test on real images on a real dataset Pix3D. The training of decoder follows deep SDF. We optimize the decoder and costly initialize the latent codes to minimize the training loss for shape reconstruction. The converged latent codes will be the ground truth for training encoder. The learned decoder gives the latent space that can do interpolation between any two latents. Then, we train the encoder with the ground truth latent codes from the training of decoder. We train the encoder to predict correct latent code mean and further output a sigma to quantify the uncertainty. We use the energy score to quantify the distance between the estimated latent code distribution and the ground truth latent code. We first present the quantitative results for monocular reconstruction. Ours gets better reconstruction with less artifacts compared with the baseline. More importantly, ours further outputs uncertainty to highlight the areas with higher errors. We show the multi-view fusion results. From left to right, we show the fused results of 1 to 10 views. The results are getting improved when more views are available. The corresponding uncertainty is also decreasing. Finally, we get better reconstruction compared with the deterministic baseline. Here is another example. The first observation is highly occluded and has high uncertainty. With more views, the result improves gradually. There is more results available in the paper. Table 1 shows quantitative evaluation on single-view reconstruction on Pix3D. We get the best performance when using ground truth mask to segment images. We also beat the deterministic baseline when using thematic segmentation or original RGB images as input. In Table 2, we show multi-view fusion results, where ours shows obvious improvements. We also propose a method called Bayesian K to filter outliers with uncertainty and keep K observations only. In Table 3, when the input images are corrupted with random crops, ours shows stronger robustness than the baseline. In conclusion, we propose an uncertainty-aware 3D object reconstruction framework with uncertainty estimation and propagation. Higher reconstruction performance is achieved. In future work, it is interesting to explore the multi-category shape prior models and explore the downstream tasks and object-level mapping and SLAM. Our follow-up work is also available. Welcome to check out. Thank you for your listening.